Okay, let's back to the RPM for faster RCN. As I mentioned in the final feature map, each point or each element is an anchor point, and each anchor point is used up to 3 scale and aspect ratio. Okay, so each anchor point, you need to try out 9 different anchor boxes. Okay. And then for each anchor boxes, then you further go for the convolution, and then finally it connect to the 1 by 1 convolution. The idea is to reduce the channel, okay? And then you will come up with 4 times 9 coordinate for each anchor point. Why is 4 by 9 coordinate? Because we have 9 anchor boxes. Each anchor boxes, you need to estimate 4 parameters or offset, okay? And then we have another branches. It's 2 by 9 scores. Again, 9. We have 9 anchor boxes for each anchor point. Why is 2? Objectless or non-object? Okay, that's it. Okay. Okay, so it's okay so far, right? Okay. Okay. So as I mentioned here, for 9 anchor, we have 3 different scales and 3 aspect ratios, and we have 2 objects, classification score, foreground or background, okay? And we have to estimate the coordinate for the bounding box, okay? Okay, then anyway, the target value, again, is calculated by the IOU, okay, intersection over union. Use cross entropy, okay? Or of course, if you want, you can use L1 or even L2 loss, that'll be fine. But most of the cases, we simply use cross entropy loss. Okay, and the offset, okay, the offset, which means delta x, delta y, okay, the delta x and delta y, okay, then we apply to get the actual RI or the bounding box, the final bounding box you use will display, okay. Okay, so that's the faster RCN. This is how it goes. So it goes like this. We input, and then we input to one single convolution neural network. Well, actually, it uses a VGG. Okay, you can use a pre-trained VGG. Okay, as the baseline. Okay. Then in the final, in the last convolution layer, based on the feature map, and each point is an anchor point, and then you apply for each anchor point, you try out 9 anchor boxes and check for the objectness. Okay, if the evidence to show the objectness, then we can go for bounding box proposal, and for, okay, this classification is a binary classification. okay? And finally, okay, actually it further go for the ROI pooling, okay? This one to check for its object not. If it's truly contain an object, then you find the corresponding location to do again to make the final classification of the class and to refine the final bounding box. Okay, so that's the final. Okay, first you will find the bounding box. This is find the bounding box, and this is the final refinement. Okay, final refinement of the bounding box. Okay, and this is just to check is object or non-object. If it's non-object, then you will skip. Okay, the proposal here. So that's why it's so fast compared with the selective search for the region proposals. Okay, let's go fast. Okay, and it look more sense, right, from here now on, because everything is based on the deep learning. Based on deep learning, it does not apply any traditional. Which might I didn't say traditional ways is not good, but it is not fast enough for real time application and not even to reach. I mean, as I mentioned, 30 up to 50 FPM, okay, frames per minute. Okay, this is about the frame rate that can be done in Paris smartphone. Okay, Tesla autopilot。OK， 好，那个特斯拉大概他们的 frame rate 就是要在这个范围，好，在这个范围才能够达到即时的应用。OK， so and here's give you some more details. This is the input. This is the baseline, VGG baseline. Okay, and then finally, after the convolution, the final convolution layer, then you go for the RPM. Each feature point, okay, each point in the feature map is an anchor point. Then you carry out 2 branches, one for object. Okay, one for object and one for the region. Okay, the possible region. Okay, and then finally it goes to the ROI pooling. Okay, and then convolution, and then finally calculate to predict the class and the bounding box. So that's it. That's the basic procedure for that. Okay. So it's quite. See that in the original model or paper, the last convolution layer is only 7x7, which means you use only 49 anchor point. It means nothing, right? But for your application, you might to change something because you might need more than, okay. I didn't mark what is the original input size here, but anyway, okay. Okay, then and for each anchor, then it will, okay, if I have a total 9 anchor box. Okay, for each anchor point, you need to try out, okay, 9 anchor boxes. Okay, 3 different scales and 3 different aspect ratio. Okay. Okay, so that's it. Okay. Let me see something. It's so the anchors I mean, in original paper, of course, you can change it, okay, for your own application. So the anchors, because each anchor point have you use 9, right? Actually, there's a lot of anchor boxes, right? Based on their object score, then it just retains the top 300 anchor spots and use it as the proposal. Okay, that's its original idea. Okay, just maintain 300 anchors. Okay, then the location, then you will be refined by the offset. Okay. Okay. The ground truth probability will be 1 if the anchor have the IOU larger than 0.7. You will say 1. Okay, that's you have a pretty good confidence it will contain an object. Okay, and if -1, which means definitely not possible. Okay, if the IOU less than 0.3 and 0 otherwise. Actually, for your own application, you might change this threshold. So in case you might ignore some of the real target object. Okay, so up to you. When you use it for your own application, you know where to change the parameters. Okay, but that's the original setup. Okay, in the code. Okay. This notation shows you, because it applies VGG 16, okay, the input size could be 224, and the final convolution layer is 14 by 14. So if we go back to look for the original size, which is 224, which means each anchor point is 16 pixels away from each other. Okay, but in the final layer, it is 14 by 14. Okay, so anyway, you can change it if the input is different. Okay, but anyway, that's why you see the red dot point here. As I mentioned, actually, each element in the feature map is an anchor point, but this shows you the corresponding anchor point in the original image. Okay, so for the case here, its red anchor point are 16 pixels away from each other. Okay, so that's it. Okay, and for the faster RCN loss function, it includes the following 4. Okay, for the loss function, first is for the RPN. Okay, RPN, the region proposal network is for binary classification to be object or non-object. Okay, it's a binary classification. So first this is very first term of the loss function, and then the RPN regression bounding box offset. It might try to find what could be the possible region. Okay, possible region, or you can think of it as the initial bounding box. Okay, and then the final classification. Okay, the object class, and then the final bounding box offset. Okay, the refinement. Okay, so it will include this 4 term as the overall loss function. Okay, that's it. Okay, so it's still quite simple to follow. Okay, I will skip this part. If you want, you can take a look in the fast RCN, and because when you find the coordinate right? The coordinate is in the higher level. It has been reduced, right? So when you want to know what is the real location in the original image, there's a lot of things you need to do. Because when you, whenever you reduce by half, for example, okay, the size may not be integer, it could be real number. Then how to find the corresponding, or find the so-called ROI, region of interest, you need to do some alignment, okay? You do some alignment. In the fast ASEAN alignment, you use a bilinear interpolation, okay, to find the region in the original image. It just gives you the example because you might have the coordinate, okay? If I give you the coordinate right here, right? The coordinate could be 1.2, 3.4, but it got to be integer. So how to find the corresponding value? Okay, this just give you the example. If you go for the binary interpolation, okay, this is the equation. 那个是内差了哈，因为二维内差就这样。Okay, in the mask ASEAN, it is more complicated. It's a lot more complicated, but it's more accurate. Okay, about the bounding box. Okay, so anyway, here's the line bounding, the line anchor boxes. Okay, you use a different 3 scale. Okay. Scale 1, scale 2, scale 3, and you have the aspect ratio. AR means aspect ratio. Okay, it's 1 to 1. Okay, 1 to 1. The aspect ratio is 1 is square. Okay, and stretch in the horizontal direction and stretch in the vertical direction. That's it. You use 9. Usually that'd be good enough. But as I mentioned here, you cannot define a rectangle rotated by 45 degrees, for example. That would be a problem. Okay, there's no way you can do that. Okay, so you need to think of, or you can refer to some of the object detection with random orientation. Okay, you need to do something like that. Okay, but here's the 9 anchors used. Okay. Okay, so I can skip this part. Okay, I already mentioned about what is IOU. Okay. So okay, just summarize the procedure for the fast ASEAN. We input an image and apply the baseline, which is existing, attempt the final feature map, and slide a 3x3 window of the feature map. Okay, pixel by pixel and for each one is an anchor point, and we try out a set of 9 anchors. Okay, like this, right? Okay. Then we do the classification with the predicted probability. This is a probability for objects. Okay, and do the regression to predict the rough bounding box. Okay, and as I mentioned, the RPM is trained with the least loss function first. Okay, this is the this is the probability. Okay, in the ROI is an object or not. Okay, it's a binary classification. The other one here is you need to calculate the regression for the true true coordinate and the ground truth coordinate and the estimate, your estimate coordinate. Okay, so that's it. Okay. The ground truth here, it says, I mentioned this here, actually, we apply for the loss function here. If the IOU is larger than 0.7, the ground truth probability, you return 1, okay? If less than 0.3, you return -1, otherwise you return 0, okay? So that you can calculate the difference of the ground truth probability and the estimate probability, okay? So, and T is the vector for the bounding box. Okay, you calculate. Then you can simply use the mean square error. Okay, L2 means square error for that. Okay, but I didn't show you here. But later on I will show you. It not just before you calculate the mean square error, you will normalize these 4 parameters. Okay, you will normalize these 4 parameters. Let me set it in case I forgot. Okay. If this is W, okay, and this is X, and this is H. Okay, and X is normalized with W. Okay. Okay. And Y is normalized with H. And then you take log W and log H. Okay, some use a square root of W or square root of H to reduce the value. Otherwise, this could be, because this value could be too small. Okay, it just do the normalization for these 4 parameters. And then you compare with the ground truth. Okay, that's how you do it. If you use the original unit, if you have a very large image, then the X or Y could be too large, right? Could be too large. Okay, that's how you do the normalization. Okay. In the code, that's for implementation. That's some engineering work. So which means when you develop your own algorithm, you must watch out, okay? I mean, the algorithm could be good. Your algorithm could be good, but it needs some fine-tune, a lot of details engineering work. It failed, not because the algorithm is not good enough, but just some of the minor details. You won't successfully train your model, so must be very careful for that, okay? But it takes a lot of experience and a lot of tedious work. Especially if you have a very large data set. When you train, whenever you change one parameter, it might run for 1 hour or even 1 day to get the result. Then you need a lot of patience to do so. And anyway, it's a tedious work for that. Okay. Okay, I might. Let me. Oh, it's right here. Okay, it's right here. Okay. I'm sorry. It should have the difference. Okay. I should say it should be delta X, delta Y. Okay, delta X, delta Y. Okay, that will be the difference. Okay, delta X, delta Y. Okay, and normalize with respect to the width and the Y. Okay, and then take log. Okay, but forget what I say. Okay, anyway, the truth right here. Okay, the truth here. Then you calculate the difference. Okay, then you calculate the difference. That's it. Okay, you do the normalization, delta X, delta Y, and normalize with. It simply take this value. Okay, this value is supposed to be 1, right? To be 1. Okay. Then the value will be 0, right? Then we try to minimize this value. Okay. anyway, okay. Okay, so I may stop here. Next week I will finish the math ASEAN and YOLO. Okay, in YOLO. And hopefully I can finish GN, okay, in another week, and then then you will have the midterm exam. I say no written exam, then you will have your oral presentation for your term project. So before Carls come, I don't know. I need to see if I can find the. Okay, assignment number 5. Okay, I tell Carls the test image should be as simple as possible, or the final work should be you can finish it in a week, hopefully. And for the written report, you don't need to write too much. Okay. Just show me the result and give me a summary. Okay, just a few pages so that you can work on your unit. But the sample, okay, the sample is the wafer image. But this you don't. The colors will give you only just in the central area. Okay. You don't need to, just like your assignment number 3, I remember. Okay, it's just central. Okay, the task is to find the gap between the wafer dot. Okay, so you can do it manually to mark. Okay, the gap here. Okay, you can do it manually, or if your assignment 3 is good enough, that's what I'm expected. Originally, actually, I wish I could have given you another assignment, which is the hot transform. Then apply to it. You use hot transform to find the gap, and then, okay, if your assignment number 3 cannot do this job, just do it manually. Okay, do it manually. But the test image that Carls provide you, some of it will rotate, okay, to some degree. Okay, so you need to just verify it. Okay, but anyway, the image it will be in the central area. Okay, and the image will be about a square. Okay, a square image, not the whole image. Okay, so that's the only thing you need to do. And try to show the IOU. Okay, show the IOU, calculate the IOU. Should be simple. So Carls will be here. Okay, will be here. We'll talk about this because. Any question about? Carl will be here show you how to run the unit and how to rotate the image. Because as I mentioned, when you train your image, you need to, some of the test image will be rotated by 45 degrees. But don't rotate the original image by 45 degrees and do the manual leveling one more time. Don't do it. Just do the manual rotation from this one. And then rotate the image and its corresponding annotate image. Everyone follow me. 你不要说我把它升准35度，然后呢，在上面重新去标哈， 直接从这里标完以后呢，这边转35度，它对应的那个东西呢，一样去转35度，知道？要用软体转好，不要自己那边没事干，然后转个5度，然后这边重新再标哈。你标只有标一次而已哈，只有标一次。Okay, but the test image will be rotated in some degree. Okay. So that's about assignment number 5. You don't need to write to, but I have a last about your term project. I'm in Carl's or Jen, my phone. Get to. Let me see if I can see it. Oh, okay, here. You can do what you are doing now, okay? You don't need to change everything. But in case you still have no idea what to do with your project, here's my suggestion. You can do this and I can accept it. And you can combine assignment number 5 with your term project, okay? But you don't have to change it, okay? Now, the only difference is here. If you decide to change your term project to this wafer die, you need to focus on the whole wafer image. Okay? You need to extend it to the whole wafer image, which means, and you know the original size of the whole image is about 7K by 7K, which is too large for UNET. You need to divide it into smaller. So you need some engineering work to think of it, how to do it. Or, for example, you divide it into 4 regions, but somewhere include the background, and you train for UNET or just one UNET, that'll be fine. Up to you, okay? And you might rotate, okay, for some degree. And the idea is just make sure you can fully segment all the wafer die, okay? You know how many wafer die here. So one of the major could be how many wafer die you can segment or identify by finding all the gap, okay? So here's you can do any one of the following 2 tasks, okay? Just select one. The first one, if you're good enough, you can just by using one, just UNET. But you need to do the automatic annotation for the whole wafer, okay? Not just in the center, okay? And no matter you go for the morphology or hot transform, that'll be fine, or anything, that'll be fine, okay? So first, focus on the automatic annotation to prepare the ground truth. So in that case, you only have to run UNET. But if this is too difficult for you to annotate automatically for the whole image, then you can go for this one. Then you can do the manual annotation. That'll be fine with me. But you need to focus on the segmentation modeling by employee UNET, of course. And one UNET variant model. I put an example here, such as U2Net or UNet++. For this application, you may not need to, but I want you to try it. And also the Deep Lab version 3 Plus, okay? The up-to-date Deep Lab. So if you decide to do it manually, then you need to compare the performance of UNet and more up-to-date UNet version, and also Deep Lab, or anything, any model, that'd be fine with me. For example, you can go for the DenseNet, or even efficient detection. Well, I will mention that next week. Efficient. There's a network called EfficientNet, and EfficientNet has been applied for segmentation called efficient DET detection. Okay. So anyway, so if you go for first one, focus on the automatic annotation. If you want to do it manually, then focus on the comparison of different segmentation tools. So that's it. But you can still work on your original project. No need to change everything. But I give it an option so that you can combine both assignment number 5 and go further, okay? For the whole image, that'll be fine with me. And for that, you can still work with your team member. You don't need to do it alone, okay? If this is the project, okay? Okay, so that's it, okay? Carls, all yours, okay? So if you have any further questions, just ask Carls, okay? Especially for the training sample and test sample, okay? So that's it.这个黎明德有 issue？
Yeah.
Okay. Okay. Any question before I go, especially about the project? So everything's okay, right? Okay. Good.
Okay, so for this assignment, you will have to install LabelMe in your computers first. You can see how to install LabelMe in the GitHub, and I easy using Python, Anaconda, and just go to your platform. I recommend using Anaconda versus the ACIS. Just create an environment, and then install the required packages and install LabelMe. That's it. How to run it? Just open the terminal and just LabelMe. That's it. Then you will have this window. So we need to open, look for image. basically we open image and then we start annotating the image. There are lots of ways to do it. I would recommend you using lines to annotate this specific image, because you can go to edit and create different shapes. For example, we can create a rectangle for each time, right? Start here and end here, and then it will ask you the name of the label. For example, you have multiple classes or objects, and we can say this is a type, right? And then we can keep adding shapes, but for this assignment we don't need we don't use the rectangle, so I would recommend you using the line, because the code I wrote for you is based on lines. So basically you will draw the line and then start marking the gaps. Insert a point here and then insert the other point at the end. Try to do it as precise as possible. Spend a lot of time doing this. This is the most important part of the assignment, basically, or the training. This is the most important part of the label. Label this and then insert the label and so on. So basically just I'll take a point here, then at the end, select the label and finish all the, but I will leave it there because it takes too much time to do this. Then you have to save it. Just Ctrl S save and try to save the file with the same name as the image. Don't change anything. The difference is that the file that you are going to save is a JSON file. It's not an image, it's a JSON file. When we save it, that's it. Now we can go see what's inside the JSON file. So what we have here is a collection of points where we draw our shapes, right? Version, who cares? Flags, who cares? Shapes. So the most important part is the key shapes. We can see that inside the key shapes we have an array with